Thank you all for attending. So I just came to Korea a few months ago, and I'm very new here. Yeah, still. I joined Sungkyunkwan as a teaching faculty here, and so this work is a joint work with Zoltan Faraday and my advisor Sasha Kostochka. This is about choosability and a slight variation of that problem. So let me just very quickly go over the preliminaries. The hypergraph H is a pair VE, where V is a set of vertices and the set of edges are a subset of the power set. It's called R uniform if all the edges have size R, and when R is 2, it's an ordinary graph that we know. The chromatic number of G, V known by chi of G, is the minimum K for which G has a proper coloring. And the list version of that problem is that a list assignment L is that you give a palette of colors L of V to every vertex, and then we choose colors from that palette, and if a proper coloring is possible, then we say that it's L colorable.
So what is a proper color?
Oh, okay, I'm sorry. So a proper coloring means that if you have an edge, then the endpoints get distinct colors. Okay.
So
in case of
at
graph,
least 2 colors per edge.
Yeah. So if it's a graph, then
I understand what it is when it's a graph, but you're
yes.
a hypergraph, right?
So that
G is a graph. G okay, I'm sorry. Yeah. So when I say graph, G is a graph here.
Oh, I see.
Yeah.
Okay.
I just mentioned H because at some point in the talk it will come across H. So yeah, and you're right that if our graph is a hypergraph, then it means the proper coloring means that it should have at least 2 colors.
Okay.
And a graph G is said to be K choosable if G is L colorable from every list assignment where the list size is K. So if you have K colors for every vertex in the list, then a proper coloring from that list for every such assignment then is said to be K choosable. And the list chromatic number, or as we call it, the choosability of the graph, is chi L of G is the minimum K for which it's K choosable. Okay. Some history. The concept of the list coloring was introduced independently by Wiesing and Erdős Rubin Taylor. For a few easy simple graphs, we know the values actually. It's for the complete graph on n vertices, both chi and L. So chi and chi L are n. It's very easy to see. I'm assuming all of you know what complete graph is. If anyone don't understand anything, please ask. For the odd cycle, chi L is 3, and for all other graphs, chi L is bounded by the maximum degree, and that's called the Brooks theorem. I mean, for the other 2 graphs, the odd cycle and the complete graph, it's not. It's 1 bigger than the maximum degree. Okay.
Also, the Brooks theorem is a list version as well?
Yeah. Yeah, it's list version also.
But is this proved by Brooks?
I'm sorry?
This is proved by Brooks?
Yeah.
Brooks is without list, right? Brooks is a name of a method.
Yeah.
And he
It's
proved the list version, or he proved the regular coloring version?
I'm not sure actually. I know that it holds for this, but I don't know. There are many proofs of this, but I'm not sure if the original one was, or they just call it the Brooks type. I mean, because of his name is there. So
I think it's Lovaas.
Lovaas could be, yeah. Okay, for the complete bipartite graph, the balanced one, the chromatic number is 2, and we know that for K33, even for K33, it can be bigger than it's 3, and actually the gap can be arbitrarily large for chi and chi L. It can be bigger than K if you take the partite sets to be of size 2k minus 1, choose K, and it's so bigger than k, meaning that you have to give me a bad list assignment for which, I mean, a list assignment of size k where from which it's not colorable. Okay, so I mean the list assignment we take is that we take all the k subsets of 2k minus 1 and put it on the list on all the vertices in one in one parted set and the same on the other parted set, and we see that it's not colorable because one part should use at least k colors, and that k colors is forbidden from some vertex in the other parted set. So okay, so we see that the gap can be arbitrarily large, and if G is planar, we know that the chromatic number is at most 4, and there are known to be there are 4 non-4 choosable graphs, non-4 choosable planar graphs. So and it's known that you can do in 5 colors. That's the Thomasson's proof. Okay, what else? Right, so now we go to our problem of choosability with separation. Now the thing is, in the original problem we allowed all possible assignments of the lists. In this problem we are going to only concentrate on the lists which we call C separated, meaning that if UV is an edge, then then the lists of U and V can have at most C colors in common. Okay, so we don't allow all the lists, we only allow the lists which have at most C colors in common. Okay, and then we want to know how the choosability parameter changes. So I mean we define this chi-L GC, where G is a graph, C is any constant. Well, constant has to be smaller than n, where n is the size of the graph. That it's the smallest k for which G is k choosable for every C separated assignment. Okay, so again in the original parameter chi-L we allow all possible assignments of the lists, and here we only allow lists which are C separated. So what do we know? It was introduced by Krathwohl, Voigt in the 90s, and they proved a few things. The first one, they proved the Brooks kind of result, that it's at most square root of this constant times C delta, and the proof is just a simple application of the lowest local lemma. I can tell you the proof, but it's just a very simple probabilistic argument. All right, that's for any graph in general. What they could show for the complete graph is that if you have a C-separated assignment, then you can always bound it in between this square root of Cn over 2 and square root of 2 ECn. Okay, and they also showed that for if G is a planar graph, then you can do it in 4 colors as long as the lists intersect in at most 1 color. Okay, so no. I mean the proof is very short actually. It's so here we are just assuming. So if you have a list of size 4 on every vertex and the list intersecting at, if you have an edge on, so yeah, for every edge the endpoints are not right. Okay, so they intersect at most 1 color, then it's easier to color, right? So okay, so what next? And they asked that, okay, so here we'll deal with the complete graph first, is that what are the asymptotics? So I mean, how does it behave with square root Cn? I mean, we see from the second bullet that it's in between square root half and square root 2e. So where does it lie as n goes to infinity? So we see when C equals n, then which means that you allow all possible assignments, which means that it should be n. But then if you decrease C, how does it behave? Is it still of the square root Cn or n over 2 or what? I mean, so asymptotics of this parameter, and we showed that it's exactly equal to 1. So it approaches square root Cn. So okay, and then we'll see the lower bound first. So in the lower bound, we need to show that right. So the parameter is at least something. It means that we need to show a bad list assignment, right? Right. So how do we show? Okay. So first we'll actually go over Krathwohl-Tusa-Voigt's proof, and then it's a straightforward generalization from there. So what they showed is that if you take a complete graph on Q square plus 1 vertices with C equals 1, then you cannot do in Q color. So every list should have more than Q colors, and assuming that Q is prime. How do we do it? How do they do it? Is that consider the affine plane of order Q, and it has Q plus 1 classes of parallel lines, right? And so it has Q square plus Q lines there, and has Q plus 1 parallel classes, and Q lines per class, Q points per line, the usual, and any 2 points. So that's the thing, that any 2 points they meet in at most 1 point, right? That's a property of these affine planes and the projective planes and all. So what do we do with this? We have Q square plus Q lines. We disregard any Q minus 1 of them, and we have Q square plus 1 lines now, and we treat them as the lists for the vertices of the complete graph. Okay, so here you have, you have your complete graph, and on them you put the lists, and these are the lines from this affine plane, and we know, and it's one separated because any 2 lists intersect in at most 1 color, and thing is that it's a bad list assignment because in the color set you have only Q square points, but you have Q square plus 1 vertices, so it's not possible to color because it's a complete graph. Any questions?
Affine. I know finite projective plane, but what is the affine? What is finite affine plane?
Affine plane. So from the projective plane, you delete one line and Q plus 1 points.
I see.
Yeah.
So it's simply.
It's just simply the grade, and then right. Okay. So the whole point is that we just took advantage of that the lines intersecting at most 1 point, and we treat them as the lists, and the color set here. The union of the color set has at most Q square colors, but we have Q square points in the Q square points to color in the complete graph, which we cannot. So it's a bad list assignment. All right. So from there, you can generalize it and show that the limit of this chi L k n 1 will approach square root n. How? All you have to do is that. You see here, we in the last slide we saw that Q is a prime, and we just we know that there is you can always find, so you take advantage of the density of primes in the integers, and then you can show that the limit tends to square root n.
But here is the bigger than Q.
Yeah. So what we do is that for any n, so you take the biggest Q, the smallest Q such that Q square is bigger than n. So you take the biggest prime Q, which smallest prime Q for which Q square is bigger than n, and then you use this, and we know that this prime Q will be what will be in between.
So my question is that you say this is bigger than Q.
Uh-huh.
It shows that the limit is bigger than or equal to 1. But like how do you show that that actually goes to 1?
Yeah. Okay. So yeah. Sure. There's an upper bound also. Okay. Yeah. Okay. So You're right. I should have. So the upper bound proof, I think I postponed it to the next slide. So yeah, I'm sorry. Yeah, you are right. Okay, all right. So I'll tell you what they did in the upper bound proof. For the upper bound, what you do is just that you consider an auxiliary graph, actually a bipartite graph, where here you put the vertices of Kn, and here you put the union of all the colors. I mean, union of all the lists. So, and you consider the vertex color adjacency graph. So if for this vertex V1, look at all the colors it's present in the lists of this vertex, and do the same for others, and look at this auxiliary graph and show that Hall's condition holds here, that you can find a matching which saturates this side, and that would give you a proper coloring. Okay, because again it's a complete graph, so you need you need a matching. So you have to show that Hall's condition holds here. I'm sorry. Yeah, you're right. So yeah, so from there you can show that it approaches square root n. But then they asked what happens when C is bigger than 1, and for that you can generalize it using a theorem of Faraday, which is kind of a similar construction as the one we did for the affine plane. All you have to do is that you have to, since C is bigger than 1, what you do is that somehow you have to group the elements of okay, so I'll come to it. So so what's the theorem of Faraday? So it's this, that if C is bigger than or equal to 1 and Q is a prime power such that C divides Q minus 1, okay, then you have a hypergraph which is H. It's Q uniform. It has Q square minus 1 over C vertices and that many edges also, and that every 2 edges intersecting at most C points. Okay, so it's exactly like the what's it called, the affine plane, except that here you have not Q square points, but Q square minus 1 over C points. Okay, so what you do is that in some way you have to by some equivalence relation you have to club the points together so that you have Q square minus 1 over C points, and that would give you that many edges also. Okay, so it's all you, so you can guess. I mean, we use this condition that C divides Q minus 1, which means that if you take the multiplicative group on FQ for F, right? So it has Q minus 1 points, and if C divides Q minus 1, there is a subgroup of this, and using that you make Q square minus 1 vertices. Okay, makes sense. So you use the fact that you have a subgroup of FQ, a multiplicative subgroup, and from that you do the same construction as you do for the affine plane. I mean, you take all the slopes and you consider Q square minus 1 edges in that way also. Okay, so this is the same construction but for general C. Okay, so how can we use this? So yeah, so from there we'll show that, I mean, from this construction we'll show that chi L of Kn or C is at least square root Cn plus 1. Okay, so what do? We take the hypergraph H that we got from the Faraday's construction. We fix a vertex V0 in that hypergraph, and let's assume that you take any bijective mapping from the vertices to the edges. Okay, which means that for every vertex you get an edge from the hypergraph that will act as the lists. Okay, not quite. You just take out V0 from the list. Okay, So here you have the hypergraph, which okay, that and you ignore V naught, and then you have some edges. Some edges are here, some are here, and they are C separated, which means that they intersecting at most C points. Okay, and assign for every vertex in the complete graph, assign one edge from here. So for this one you assign, this is the L of V1 and so on, except that if you have an edge which intersects V naught, you ignore that. Yeah, I mean so not ignore, you take away this point from that list. Okay, all right. So then what? Then we get that the list size at least Q minus 1 is C separated, and the union is exactly N minus 1, which is smaller than N, and hence you cannot get a good coloring. Okay. So again, just showing that it's a bad list assignment. Okay. All right. So that's the lower bound. For the upper bound, as we saw, that we'll show this, that you take the vertex color bipartite graph. I mean the vertex color adjacency graph, but it's a bipartite graph, and show that, and it's an observation that Kn has a proper K-list coloring if and only if our auxiliary graph has a matching. I mean, which saturates A, which is the vertex side of the bipartite graph. Okay, right. So and just one small other thing that we'll actually come across this, the Johnson's bound will be useful here while proving the upper bound. It's just that if you have M sets and each of them size K, and each of them have intersection at most C, then the union has to be large, and it's at least that large. Okay, that's the Johnson's bound from set theory or coding theory or whatever you can call. Okay, so now what? So with this, so we'll show this that if n is at most that much, then chi L Kn C will be at most Q plus 1. Okay, and how much time do I have left?
Half an hour.
Half an hour. Okay. So again, so we have to show that that Hall's conditions hold. So we'll have this again, our bipartite graph, the auxiliary one. So you have the lists, the vertices of the complete graph here, which is part A, and part B is the union of all the lists, and you have bipartite graph. And what do we show? So again, so you have to show Hall's conditions. So for any subset S in this part, you consider the neighborhood set N of S, and you take the induced subgraph on them. Okay, and assume that you have a color alpha here, and if the degree of alpha is smaller than Q plus 1, it means that it's present in a few vertices, then it's clear that Hall's condition will hold, because I mean, just count the edges and it will hold true. If not, if it's bigger, then you can also show that we'll arrive at a contradiction, because we'll contradict the fact that n is at most that by the Johnson's bound. Okay, so in both cases, so either you arrive at a contradiction or Hall's conditions hold, and that would show that, I mean, that would show this upper bound. Okay, so this implies right. So we showed that it's I mean, so you see this at most half plus square root Cn, and we also showed that it's at least square root Cn. So that shows that the asymptotics is square root of Cn. Okay. Any questions so far on the complete graph section? Okay, so then let's move on to complete multipartite graphs. We have already seen this, that the gap between chi and chi L can be arbitrarily large, and this immediately tells us that chi L of kmm is at least half plus small o of 1 of log m, because if you solve for k in terms of m, then you get that. Which, I mean, so this was a bad list assignment, right? So this was a bad list assignment with this. So if you solve for k in terms of m, you get that. So it means that with this as the list size, you cannot have a proper coloring. Okay, but the question is, can we do better? Well, by probabilistic argument, we can show that it can be the chi L of kmm can be bounded by log m, but it's upper bounded by log m is the lower bound is half log m. So where does the truth lie? Well, for that, actually the old theorem of Euler, Rubin and Taylor comes useful, and that's how they showed this, that if you have, so it's a relation between two parameters, mk and nk. And what's mk? Mk is the minimum edges in a non-two colorable k uniform hypergraph. Okay, so you take a k uniform hypergraph which is non-two colorable, so you cannot color it in two colors. Okay, and the smallest number of edges in that. And nk is the minimum order of a non-k choosable bipartite graph. That's what we want, right? That you want, right? So we are looking for non-k choosable bipartite graphs here, right? That so we want the value of k here. So and they showed that that this nk is bounded by mk and twice mk. Now, why is it? Because okay, we'll come to this proof afterwards, but this is true. Okay, that so you have two worlds here. One is for in the bipartite graph world, and the other is the uniform k uniform non-two colorable hypergraph world, and they're related in this way. Okay, so a non-two colorable k uniform hypergraph and a minimum order of a non-k choosable bipartite graph. Okay, and so what okay, so I just tell you what the idea is, that so if you have a non-k choosable, so if you have a bipartite graph with, say, you have nk vertices here, nk vertices there, right? Okay, and what will, so if it has to, okay, non-k choosable, so it means that that you want to give the the list size is k. Okay, I mean, you have to give a bad list assignment with list size k, right? And the lists will come from this non-two colorable k uniform hypergraph. Okay, how? So here you have this H, which is non-two colorable, and k uniform. Okay, now what does it mean by non-two colorable? It means that whatever partition you give me, there will be some edge which escapes the partition. It means that you cannot cut every edge, which means that there will be some edge which escapes it, which means exactly, it means that you cannot give a two coloring here. It means that you cannot tell that that color is going to be present here, and that color is going to be present there. So there is one edge which will escape. It means that it will have all the colors as one and not twos, which means that all these colors must be used here, but this edge is on this part, so you cannot use it. Okay, so and you see the order is 2 times mk, right? And that's why you have the inequality nk is smaller than 2 mk. Okay, so so that's the idea, and Erdős has actually proved it in the 60s that mk is bounded by this. That's the very first application of the probabilistic method, I think. So he showed that there is a hypergraph which is k uniform non-colorable with about k squared 2 to the k edges. Okay, and from here, if you solve for k from here, you get log m. I mean 1 plus small o over 1 of log m, right? And alone or by any probabilistic argument, you can also show this thing. So we actually showed that chi L kmm is actually 1 plus small o over 1 of log m. Okay, so the first example was a naive example, a very straightforward one. The second one, which Erdős, Rubin, and Taylor showed, from this construction you can get a better bad list assignment. Okay, so and which shows that the asymptotics of chi L kmm is log m. Okay, so that's the classical problem. Now, how do we use it in our case where we have the C separated assignment? Okay, so here we are not allowing all the lists again. We are allowing only the lists which have only C colors in common. Okay, actually it turns out, it's surprising that even for C separate assignment, it's still the same asymptotic, still log m. Okay, so we saw for the complete graph it was not, it was about square root C times n, but in this case for the complete bipartite graph is the same. So that's kind of surprising, or something we did not expect, I think. Okay, so how does it work? The upper bound is obvious. I mean, chi L km. So if you have a C separated assignment, it's smaller than chi L kmm, because with C bigger than 1 it makes it easier to color. Okay, so that's just a forward. So we have to just show that the lower bound is true, right? That okay, so yes, so we have to show the lower bound, that chi L kmm C is at least log m, okay, asymptotically. So how? So we need to understand what Erdős, Rubin, and Taylor did. So I told you this theorem already, and what he showed is that there exists a k uniform hypergraph on n vertices with at most k squared 2 to the k edges, and he actually showed that the independence number is at most n over 2. Okay? I mean, and that would imply that that the chromatic number is at least 2. Okay, so okay, so that was so that's this construction here. Okay, so we have to do some kind of similar construction, that in our case if we want C separated ones, then how should we do it? So right, okay, so we, I think, still on that proof here, right? So the first proof was so I'll here show you a proof of the construction. So the first proof which Erdős gave was probabilistic construction. The second proof, or there is another proof by Lovas, and it's not, well, it's not okay. So the way it works is this. Right. So again, so you have 2k square vertices here. So you have 2k square vertices, and we'll show that the edge set of H is about the order of k squared 2 to the k. Okay, and that the independence number is smaller than n over 2. Okay, so how did he show it? So what he did, okay, so let me erase this part. So you consider a set S of 2k square points. Okay, so you have this the base set, and from here we are going to consider or make an auxiliary hypergraph, a very big one. And what will be those? So you have the 2k square vertices. We'll make an auxiliary hypergraph here, a big one where the vertex set will be all the k tuples from here. Okay, so all the k tuples that you can form here is going to be there. Okay, so it's a very huge graph, right? So the vertex set is 2k square choose k, right? That's the vertex set. And what are the edges? So the edges will come that from here, so that any partition you do for in this part, call it x and y, you take all the k tuples you can take from x or y only, so which are only in x or only in y. Okay, those will be the edges, right? So you have many small k sets here and many small k sets here, and right. So for every partition P you have an edge EP there. Okay, now right, and then you see that the transversal of this so the what's it called, the vertex cover or the transversal number of this new auxiliary hypergraph will give us the size of the hypergraph that we want. Why? Because so any transversal you take, so transversal means that you pick, so from it's a what's it called, edge cover, which means that a set of vertices which, so that every edge has one vertex from that cover, right? So how to put it, I mean, it's a transversal. It means that it's a set of vertices such that every edge will have intersection from that set. Okay, so every edge has a representative in that set. So, and why is it so if you take those vertices, which are actually edges in our hypergraph that we want to build, will be of the required size that we want, because or at least will have the property that it's that chi h is at most n over 2, because you see because the way we build the sets was like this, that for every partition we take all the k tuples, so it has a representative. So if you want to actually to color this new so the hypergraph which we build from taking the transversal will not be too colorable, because we took all possible partitions here and we have the representatives in the new hypergraph. Okay, so from here to auxiliary, and from here we are going to build our graph H. Okay, so we take all the transversal sets, the vertices. Okay, so that gives the required size, but sorry, that gives the required H. But then what's the size? The size you can count by this identity, that we know that the transversal number of a hypergraph is at most 1 plus log of delta times the fractional 1. Okay, and that is at most and if you count properly or estimate it properly, that will give you the required size of the hypergraph. Okay, so that tells us right. So how do we use this? In our case, so in our case, so let's make things easy. Let's keep C to be 1. Okay. So we have one separated assignment. So we want a one separated assignment which has this property that so we want two hypergraphs which we are going to place on the vertices of our complete bipartite graph, but they should be such that they should be nearly disjoint. It means that any edge you take from here, any edge you take from here will intersect in at most one point, because we want the C separated one, and that it should have low independence number, like we did for this problem, for the original problem. So we have to build these two things, and right, and we show that it can be done, and it can be done in at most k to the 4 to 2 to the k edges. So you can have the required lists, and you will have you are going to have k to the 4 2 to the k lists in every partite set, and we have the required thing we want, that the independence number is at most n over 2, which exactly tells you that you cannot two color it, because anytime you want to two color it, so it means that so these two hypergraphs h1 and h2 have the same vertex set. So you have a vertex set here, and you have you have h1 here and you have h2 there also. You have two hypergraphs which are nearly disjoint, so they are kind of orthogonal to each other, and has a property that anytime you make a partition, you're going to miss an edge from both of them, and that would translate to that you cannot two color here. Okay, so I'll not talk further about it, but that's it, and that would tell you that that's the right asymptotics, that you get log m there. Okay, so if you have an L-partite graph with part size m, then it's log m to base L over L minus 1. So when L equals 2, you get log m to base 2. Okay. Okay. So any questions? Okay. Okay. So how do we? Right. So that's for 2, but then we can actually. So how do we build it actually? So I mean we just told that we want these two hypergraphs, but how do we build it? Right. So the building is actually iteratively. So what we do is so for the first hypergraph h1 that we want to build, we are going to take so we are going to take 2k square sets. Okay, so we have 2k square sets, and okay, so and on each of them we are going to put the hypergraph which Erdős built. Okay, so it's a disjoint copy of those graphs. Okay, and now from here we are and then we are orthogonally going to choose the edges for the second one, that we are going to pick one vertex from here and one from there in such a way that we keep the independence number low and also have the edge set low, I mean the edge size low. And right, so that's what we want. So we start with this, and we iteratively and then right. So if you have three parts here, then you take again that many copies of the older graphs, and you orthogonally choose new edges. Okay, and it actually the proof. Why can we do this? with low independence and low edge size is exactly the Loess's proof. What he did. So what he did is that instead of sets of size that big, he took, I mean, original proof is with sets of size 1. I mean, here we have this, we take 2k square sets of size t each. What he did was, okay, when t equals 1, you have 2k square points, and on that you are going to build the hypergraph. So the same technique, we just adopt his proof for, instead of 1 point, we take sets of size t, and all the calculations will follow. Okay, so that's it. So it shows that it can be done. Okay. Okay, so that's what I wrote here. There's this iteration. Okay, so I hope you understood this part. Okay, now for hypergraphs, we'll not go into detail, just tell you what it is. So if you have this KLLM is the complete L uniform L-partite hypergraph. Okay, and each partite set has size m. Then this is also true that it's still log m to base L as it is for our original parameter chi L. Okay, so in this case, so if you have L partite L uniform hypergraph, it's also true. Okay. Okay, so I think that would be most of it, and open questions, a few of them. The first one is actually, so this parameter chi L GC, we don't know if it is monotone, because the way it is defined that, okay, so if you have induced subgraph, then it's clear it's monotone, but if it's not induced, it's not clear, because the lists for H is not a proper subset for the list of G. Okay, because if you delete an edge, then you can have other lists which are not in for G. So we don't know examples yet. So we know examples of hypergraphs that it's monotone. So it's not monotone, but for graphs we don't know. Okay. So we have very small examples of hypergraphs for which it's not true, but for graphs we still don't know. But we still think that the complete graph is the worst. But we can't show, because we don't know if it's monotone. Okay. Next one is, okay, find it for other classes of graphs and hypergraphs. I don't know which one to pick, because in the literature, even for I mean the choosability of other class of graphs is not known much. I mean, it's we just know it for maybe Kneser graphs and few other. Yes, but it's very hard to do it for other hypergraphs, graphs and hypergraphs. So I don't know which one to pick next. And this one is kind of the biggest one. I think that if you allow lists of size 4, but the intersection can be 2, at most 2, then what? So we see that if the intersection is at most 1, then it's a short proof, but for 2 we don't know. We try to think about it and try to adopt Thomason's proof, but I mean it uses induction, and for that because we don't know if it's monotone or not, so we cannot adopt the same, or maybe some clever technique, I don't know. The last one, okay, somebody asked me this one, characterize all graphs which are, okay, so you give the list of size 2 and intersecting at most 1. So which means that if there is an edge, the lists are distinct. So Erdős, Rubin, and Taylor in their paper, they characterize all 2 choosable graphs. So it is slightly different. That okay, 2 choosable, but with the restriction that the list can be just. intersecting at most one color. And for the fourth bullet, why it makes sense to ask this is because all the non-4 choosable graphs have intersection intersect, right? So if how to say it? So they right, if there is an edge, then the lists are not the same. So if right, so that they intersect at most. Wait, what am I going to say?
You mean the all non-choosable planar graph?
Planar graphs have
edge with intersection and list three.
at least 3. Yes. So it makes sense to ask for 2 in that case.
So you think it's positive or negative?
We have no idea. No idea. We just tried to think with someone for some days, but
So how big are these examples of the
non-choosable.
planar graphs?
One, I think the smallest one with 64 vertices or something.
Oh, okay.
So I think.
Think of 100.
No, I think 64. The Mirzakhani graph, I think. Who knows? You know, I forgot the construction, but. But.
I know the first, I know.
Yeah, I think 64 vertices or 63 but 60. Okay, I have to check, but yeah. So okay, that would be all for us.
Any questions?